We are moving on now to carbon-13 NMR. Okay, this is still nuclear magnetic resonance, but now we're going to focus more on the carbon nuclei. So first of all, why carbon-13 and why not carbon-12? Well, carbon-12 has no magnetic spin because it is an even number. Carbon-13 has a magnetic spin. Okay, so you can see carbon-13 in the NMR. The problem with carbon-13 is that it's only 1% of the isotope, okay? And so if you look at a hydrocarbon, which may have 4 carbons in it, and think about 1 mole of sample, which is 6.02 times 10 to the power 23 atoms in there, then 1% of that is going to be carbon-13, okay? So which means you're working with a lot fewer atoms of carbon than you were with hydrogen, because for hydrogen, it was H1, which is also the most abundant isotope, okay, in there. So carbon-13 is a little bit harder to work with for that reason. The signals are going to be a little bit weak and they get lost in the noise sometimes. So what that means is you need to have a really concentrated sample so you can work with a large number of carbon atoms in there so you can actually see your sample. And the other thing is about 100 of spectra being taken. Now in this case what it means is that you have to leave your sample running for a long time. I never mentioned this in the proton NMR presentation, but it takes about 10 to 15 minutes to run a proton NMR. If you have a nice concentrated sample, 15 minutes is enough. Carbon-13 on the other hand will take a lot more time because what happens is the magnetic field has to keep reading the nucleus in there, and it has to keep reading and it can't get it. So it takes a long time to get the spectrum. So sometimes you have to spin your sample in the magnet for about 10 to 12 hours before you get anything at all. So carbon-13 is a little bit of work, okay, in order to get a nice spectrum. This that you see here is it's a typical carbon-13 NMR. Look at the scale. It goes from 0 to about 200. TMS is still there. You need a point of reference. So the TMS is still there. And this little dash lines over here, okay, this is the baseline. And the baseline here, this is little noisy, okay. And the noisy thing is because of the diluteness of the sample. If the solution is very concentrated and if your NMR is a good NMR, for example, 400 megahertz or above, then you will not see so much of noise, okay, in there. A lot of the NMR spectra that you see in these presentations, they're coming from textbooks, of course, and most of those textbooks have spectra for 300 megahertz NMR or 400 megahertz, usually 300 megahertz, okay? And so for proton, it works fine, but for carbon-13 NMR, you will see this noise, okay? Now, the way the NMR works is the same, the way the carbon-13 NMR works is the same as proton. So if you have different types of carbon in there, that's the number of signals you will see. So here in this structure for 2-butanone, you have 4 types of carbon in here. So you will see 4 different signals. Now remember what I just mentioned about carbon-13. Carbon-13 is a very small amount of isotope. The only way you will see this carbon over here, the CH3 here, is if there was a carbon-14 here at some point, okay, which there are because it's 1%, okay, of the sample. So you might have it, but then for the NMR to actually see it, you will need to run it so many times so it can see it and give you a good signal for it, okay? And so that is what we mean by carbon-13. So if you have carbon-13 here at any given point, that's the only time you will see the signal. If there was no carbon-13 on this carbonyl carbon, you will not see that signal, okay, at all. So that's what it means by a carbon-13 NMR. All right, so here you have 4 different carbons, so you see 4 different signals. The signals appear in the same way as they did for the proton NMR, which means that you have the shielded region and then you have the de-shielded region. Carbon number 2, which is the carbonyl carbon, is the most de-shielded carbon, so that's where it appears. It's on the most left side. Carbon number 4 is the most shielded one, so it appears on the right hand side. So the pattern is pretty much the same, okay? And it's also interesting to see that the carbon peaks that you see here are all going to be singlets. You will hardly ever see any coupling going on, okay? And the coupling doesn't occur because, yes, think about it. The coupling does not occur because you can never have, it's very hard. You can hardly ever have two carbon 13s next to each other. Okay, that's the only time you will see coupling. All right, so anyhow, for most of the carbon 13 NMRs, you will see what they call a broadband decoupled spectrum. And so decoupled means that even if there was by any slight chance, like a micro chance or a nano chance that there was a carbon 13 next to another carbon 13, it would be decoupled, okay, by the time you see the spectrum. This spectra here, this is very interesting because this is what we do for carbon 13. You cannot do this for protons, but you can do this very easily for carbon 13s, and this is called a DEPT. Okay, and what a DEPT spectra does, it separates out the primary, secondary, tertiary, and quaternary carbons. Okay, so this one here is for 1-chloro-2-propanol. So in 1-chloro-2-propanol, what it has done, it has separated out the CH, the CH2, and the CH3 signals. Okay, so if you look at the total NMR, you will see the 3 signals. Okay, but if you separate it out, you can see how many different signals you have coming from primary, secondary, and tertiary. And it doesn't have any quaternary, otherwise it will give you the quaternary carbons also. So that is really the neat thing about carbon 13 is if you have a large molecule with 20 carbons and you're seeing 20 peaks there, then you really have no idea what's going on because there's no coupling going on and you can't tell which carbon is what. But if you do the DEPT on it, all those 20 carbons will be completely separated out into the primary, secondary. It makes makes interpreting the carbon 13 a lot easier. This little peak that you see here, okay, this is for CDCl3. You have never seen the solvent peak before. Or the only peak you have seen before is the TMS peak, all right? And we put the TMS in there because we want the 0 mark there. You've never seen the CDCl3 peak before because the sample overwhelmed the solvent, so you would not see the solvent. But now that we're talking about carbons, this carbon is also capable of being a C-13, and so that's why you end up seeing a little bit of the solvent peak here. Okay, so you will see that around 77 or 78 ppm. Here is a comparison of the hydrogen and carbon chemical shifts, and you will see some patterns over here. The scale is from 0 to 10 for proton. It's from 0 to about 200, 220 for carbon 13. The aromatics come around 7 for proton NMRs, and the aromatics again come around 150. So they're kind of right below each other, okay, when you think about where the chemical shift might be. All the alkane carbons will come very much upfield, just like in case of hydrogens. So the carbonyl carbons are going to be the most downfield shifted, which they are found around 200. In case of proton NMR, you will find the carbonyls also downfield shifted, okay, like the aldehydes and the acidic protons. So there are some patterns here. I wouldn't memorize these patterns except for the 2 or 3 that I've mentioned to you because those are the key and they will not change in any way. But the other things can change. Methane protons and methyl protons, they can change if you have any electronegative group around it. Okay, so I wouldn't memorize those ones. In some cases, depending on what kind of research you are doing, you can actually work on what we call a combined carbon and hydrogen NMR. Okay, and so you can see your proton as well as your carbon NMR right at the same place. So you can tell right away that, oh, I have a aldehyde carbon and here's my aldehyde proton. So you can run them concurrently, and then actually you can't run them concurrently. You have to run each of them separately and then combine them. So depending on your instrument, you should be able to do this. One thing I should also mention to you is that when you do carbon NMR, you have to change something in the instrument, okay? Proton NMRs are run with a different probe, as we call them. The probe is the sample holder, and the carbon 13 is done with a different probe, with a different sample holder. So when you switch from one to the other, you have to change the probe. And so once you change the probe, that's how you get the different spectrum. You can use the same machine for both. By the way, you cannot use the same machine for, say, fluorine or phosphorus. Those need a completely different kind of a machine, but carbon and hydrogen, they can be run on the same machine, but with a different probe, okay, or a different sample holder. So at one point, what you will do is you will run your proton NMR, which can be done in 15 minutes, and then you'll change the probe and you'll put your sample in the carbon-13 probe, and then you'll run the carbon-13 NMR, and then you will take both of those two and combine them to give you something like this. Okay, and so you can run, you can have both of the sample displayed to you. And then we have this head core. Just like 2D NMR was fun to do, head cores are also fun to do. Okay, because what you can do now is on one scale, you can run your carbon NMR, on the other scale, you can run your proton NMR. And again, just like as if you're flying over a mountain range, you can then correlate which proton belongs to which carbon. And so this is really fun because it makes so easy to interpret your NMR then, okay? Carbon and hydrogen head core, they take a little time to run. Sometimes they can take up to even 15 to 20 hours to run, okay? Because you got to correlate the two things. So they take a little time, but the results are really very satisfying, okay? And this is especially true when you have complex molecules and unequivalent hydrogens where you're just not able to place them. Then it's much easier to run a coupled NMR, and then you can go ahead and then draw lines and then see how things will correlate to each other. So this proton, for example, belongs to this carbon, and so on and so forth. So head core is really fun to do. The spin-spin splitting, I already mentioned to you that it is very unlikely that a carbon-13 would be next to another carbon-13, so there is no splitting, which is, in some ways, it is a boon in disguise, so that way you don't have to worry about any kind of coupling going on. So the carbon-13 sometimes will couple to the protons, and that's why you have to run the decoupled spectrum, okay? And so you don't want to run carbon-13 with proton. It's really hard to then interpret the spectrum. Interpreting a carbon-13 spectrum is really quite easy to do. All you have to see is the number of different signals that you see. Now remember again, if you have a symmetrical compound, then you will see less number of carbons. But just because you have less number of signals does not mean you have less number of carbons. It just means you have symmetry in the molecule. It's possible. So for example, a molecule like cyclohexane will give you only one signal, okay, but you have 6 carbons, but all those 6 carbons are equivalent. So you use the same kind of thinking that you had for proton NMR for carbon-13 NMR also. And the location, the chemical shift, okay, this works the same way as we did with the proton NMR, which means that you have the downfield shift and the upfield shift, depending on what functional group you're talking about. The peak areas, they will indicate the number of carbons in there, okay, so you have to do the integration again, and then you can figure it out. So this way, if you have symmetry in the molecule, you can at least tell the ratio that you have in there, okay, and then in cases of where you want to run the coupled spectrum, then you can tell the number of protons attached to the carbons, as we did before. So here again is the carbon-13 for 2-butanone. Now you will look at it from different eyes, hopefully. So you have the 4 signals, the downfield shifted, the upfield shifted, and so on and so forth. So here are a few problems for you to work on, and I will not tell you anything about this, okay? I can give you a little clue to get started, but that's all that I can do. So if you have C5H11Br, it means that you have 5 carbons you're working with. But if you have 5 carbons and you're seeing only 4 signals, it means that 2 carbons must be alike. They must be in the same or they're equivalent, as you want to say. So then you need to kind of draw different constitutional isomers for C5H11Br and see which one fits this model. Okay, here is another C5H11Br. Okay, so these two are spectra of constitutional isomers, and in this case you have 4 peaks again, but these 4 peaks are so different than these 4 peaks. Okay, the other thing about these peaks is that you don't have a DEPT spectrum, but at least it's telling you you have a CH2 and a CH2 and a CH. How much easier can it get? Okay, and here you have a C, so which means you have a quaternary carbon here. So it makes it easier to interpret the NMRs a little bit. Here is another one also, same compound, okay, different constitutional isomer. A little bit about Fourier transform. Okay, we talked about FTIR. Fourier transform is a calculation that is done to improve your signal, and that is exactly what Fourier transform NMR is. So if you ever see FT-NMR, that's all it is. It's just Fourier transform, which makes it a little bit easier to interpret your spectrum. Okay, and so after a whole bunch of calculations, the signals are converted into a nice, neat little spectrum for you to run, okay, or to see. So it makes it a lot easier to interpret your spectrum. But otherwise, don't worry too much about the FT part. You will need this only if you are really getting into instrumentation development. So your key concepts for carbon-13 NMR is, of course, know the chemical shifts, where all the carbons are going to appear. You should be able to interpret a carbon-13 NMR. Of course, I will give you the molecular formula. Sometimes I don't do that. If you have a really small molecule, then I'll just give you the spectra. You figure out the structure yourself. And then, of course, you should be able to predict how many signals you will see for carbon-13, which one will be downfield, which one should be upfield, and so on and so forth. So you will never get a head core or something like that from me, okay?